So we're going to begin Chapter 5. Chapter 5 is entitled The Transcendental Functions. Uh, we're not going to do all of that for this class. We're going to be looking at the natural log and the exponential base e function. Uh, and use those to maybe think about other logs and exponential functions. Also, under transcendental functions are the hyperbolics, trig functions, hyperbolic sine, hyperbolic cosine. We are not going to get into that. You will get to the joy of that in your next calculus class, I am sure. But we're going to start off with section 1, 5.1, is on the natural log, and look at differentiation when we talk about the natural log function. So we're going to develop and use properties of natural logs, understand the definition of number e. Now, this is not going to be, you've looked at natural log and the number e in your pre-calculus and your algebra 2 classes. And we've just looked at those basically from starting off with defining the exponential function and the log function, playing with it that. We're going to take a different approach here and define these functions as they apply to calculus. And we're going to see that they do actually end up matching with our other definitions. But we're taking the calculus route towards this, and to see how we can use derivatives using the natural log function. So, why did that just do that? I see why it did that. So, to start getting a little background, why are we doing what we're doing? One of the favorite rules of any calculus student is the power rule. That's one of the first rules we learn when we start doing derivatives, and it makes our life oh so happy, oh so much better when we have to deal with calculus. That is. But when we got to integration, we have one slight problem, besides hitting the wrong button. Because the integral of x to the x to the n is going to be x to the n plus 1 over n plus 1, but that's not defined when n is equal to negative 1, because if we do that, we get a divide by 0, which is a big no-no, right? So we cannot do the integral of x to the negative n, or negative 1. We cannot integrate 1 over x. This is a problem. So, as I have written here, what do mathematicians do when we run into something that doesn't make sense, that's not defined? We make something up. You know, this came up when you come up to say, what does it mean to take x to the 0 power? X to the 0 power just does not make any sense. So we define it as 1 and then see if it works with our properties of exponents. And happily it does. But what we're going to do is just figure out, well, what's the antiderivative of 1 over x? Let's make something up. So, and I did that again because my button's at the wrong spot. Okay, here we go. So we're going to define this integral, the integral from 1 to x of 1 over t to t, and define that as the natural log of x. This is basically the calculus definition of the natural log. Now, the domain of a natural logarithm is going to be the set of all real positive numbers. This is what the graph of, well, this is the graph of y equals 1 over t. And let me get my pointer up here. As you look, if x is a number bigger than 1, then the integral from 1 to x is going to be a positive number. Because this is always, 1 over t is always going to be positive as long as t is positive. So this area is going to be positive. But if I pick x as a number less than 1, then I'm doing the integral from 1 to x is going to be the opposite of the integral from x to 1. So this area is positive if we go from x to 1. Since we're going to 1 to x, we get negative. So over here we get positive values. Over here we're going to get negative values. I guess I have this all written out here. I always do. I look this over and then I start working through and I forget, and it's got like, I have all this in here. X is greater than 1, the natural log is positive. Less than 1 is negative. When x equals 1, because again, the integral from 1 to 1 of anything is 0. So we have that. Hey, that kind of sounds like logarithms, right? And if I pick an x value that's less than 0, this graph of 1 over x is not continuous. So I could not take the integral from 1 to x if I am over here, because I have an asymptote. So it's undefined on the interval x to 1 if x is less than 0. So that's why we can say, okay, my domain is going to be 0 to x, or is greater than 0. We can't be 0 because that's, again, where the asymptote is. The range is all real numbers because I get positive numbers this way, I get negative numbers this way. So this is what the graph of the natural log of x looks like. So again, the natural log of 1 is 0. If I'm greater than 1, I'm positive. If I'm less than 1, I'm negative. This comes down to an asymptote at the x-axis. Continuous, increasing, 1 to 1, concave downward. So this is, if we use this definition of an integral of 1 over t dt, we get something that acts just like our logarithm functions that we learned by saying, hell, the log, what is it? It's just the inverse of the exponential. That's the way we had introduced it before. But now this ties in and fits in with what we're saying calculus-wise. So I'm not going to prove these. These are these properties that you were given in pre-calculus. You're given in algebra 2, hopefully. The natural log of 1 is 0. Any log of 1 is 0, because anything to the 0 power is 1. The log of a times b is the log of a plus the log of b. The natural log of a to the n is n times the natural log of a. And the natural log of a over b equals the natural log of a minus the natural log of b. So if when we multiply, we add, we divide, we subtract, do the opposite, do the opposite. It makes sense. But again, on all of these, a and b have to both be positive. N has to be a rational number. So see if you can use your skills, what you've done before, and expand these out. I'll give you a second. Try to do it on your own, then come back and see what I got. Whoops, let me go back. So you can see the problems. So again, we kind of use the order of operations backwards. So first we're going to undo the, well, actually, I'm going to rewrite this as the natural log of 2/5 x to the third. So I'm going to say that's the log of a product. So that's the log of 2/5 plus the log of x to the third. And here we have an exponent. So we can have that's the log of 2/5 plus 3 times the natural log of x. That would be expanded out. Make it as simple as smallest chunks as possible. So in this one, I'm again going to say this is 2x minus 5 to the 1/3 power. So this is just 1/3 times the natural log of 2x minus 5. Isn't that great? We got rid of the third root. I like getting rid of radicals, right? Okay, this is what I was trying to talk about before. This is going to take a few more steps. I'm going to first take care of this division. So that's going to be the natural log of 2x plus 1 cubed minus the natural log of x times, let's write that in exponential form, x squared plus 7 to the 1/2. This one I can pull down my multiple. Three times the natural log of 2x plus 1. Here I will, this is a product, so I have to make this a sum, which means I gotta do that before I do the subtraction. So that's going to be the natural log of x plus 1/2 the natural log of x squared plus 7. So we're going to end up with 3 times the natural log of 2x plus 1 minus the natural log of x minus 1/2 the natural log of x squared plus 7. This is the one thing you got to be careful of when we're expanding these. If you have a product in the denominator, you're subtracting a sum, so make sure you don't lose that negative sign. But yeah, did a bunch of this back when you're learning about logarithms and the properties of logarithms. It makes this a little clunkier, but we're going to see how it's actually going to make things a little nicer for us when we start getting into doing some of our calculus ideas. Okay. So now when we first started studying logarithms, we defined them in terms of the base. So we always said the log base something, so the common log is base 10. So the natural log has to have a base also. Has to have a unique real number that the natural log of that number is going to equal 1. So we can do that by going back to, and I'm not actually going to go through and do that. We just have to start with our at 1 and keep going until we get a point where the area underneath this curve between 1 and whatever that number is 1. We can just do that trial and error and keep working on that. Eventually we get to that. And we get that number, that magic number, 2.71828182846 ... It's an irrational number like pi. And again, we talked about E in pre-calculus. We talked about that. We kind of waved our hand. Where does E come from? And we say, well, E is this number that shows up in a lot of places. Well, you can define E if we define that natural log using the integral idea and say, what is that number that integral from 1 to E of 1 over t dt is going to equal 1. Oh, this is just jumping ahead on me. So we're defining E as the number that if we take the natural number log of E, we get 1. So they kind of tie in. We're kind of going an opposite way of defining it. Before we have calculus, we just say, here's what it is, trust us. Now we're seeing a little bit more, where does that come from? But the sweet thing is, oops, I'm going backwards. If the natural log of E is this integral of 1 over t dt, then if we're going to take the derivative of the natural log, and derivatives and integrals are inverses of each other, the derivative of the natural log of x is going to give us that 1 over x, because that's what we were taking the integral of. And so the derivative of the natural log of the function u is going to be 1 over u times du dx, or u prime over u. And that makes a natural log pretty nice to differentiate. So let's give this a try. Again, try it on your own, or maybe go through an example and then pause and see if you can do the rest by yourself. And I got to quit doing that. Clear off that. So if this is my u is 3x squared, u prime is going to be 2 times, it's going to be 6x. So the derivative of the natural log of 3x squared is going to be u primed over u, or 6x over 3x squared, which is going to be 2 over x. I don't quite like that color. Let's go to a different color here. Derivative of x times the natural log of x. So here we're going to have to use the product rule, because this is x times something. So we're going to say derivative of x is going to be 1 times the natural log of x plus x times the derivative of natural log, which is 1 over x, which is going to be the natural log of x plus 1. This case, we're taking the derivative of the natural log of x cubed. Here we're going to have to do the chain rule. So we're going to take 3 times the natural log of x squared times the derivative of natural log, which is 1 over x. So this is going to be 3 times the natural log of x squared over x. Finally here, this is again kind of like this first one. It's pretty much a chain rule thing. Here's my u is x cubed. So my derivative of u is going to be 3x squared times 1 over x cubed is going to be 3 over x. Sweet! Now, when we talk about logarithms, one way logarithms were originally developed, one of the major uses used to be was to make calculations simpler. Because we look, the log of a product is the sum of the logs. So we can take multiplication and turn it into addition with logarithms. The log of a number to a power is just a multiple. We looked before and we said, hey, when we took the log of the cubed root, it was just 1/3 the log of the value. It's easier to multiply by 1/3 than to take the cubed root. So with this idea of using logarithms, it could make a lot of complex calculations simpler. We don't need that anymore. We've got calculators. But it does help us when we start doing some differentiation. Because when we're going to look at this, I'm going to take the derivative of the natural log of the square root. So I rewrite this in exponential form. Oh, wait. This is the log of something to the 1/2 power. That's 1/2 times the log. I simplified that up. Oh, that's the constant multiple, so it's 1/2 times the log of x plus 1. And now, oh, that's just u prime over u, and u prime is 1 in this case. So we got 1/2 times 1 over x plus 1. And that's kind of how we can use some of these properties with logarithms to make some problems easier to do. So for example, this one, this looks like, if I'm going to say u prime over u, just think about that. U prime is a mess. To do the derivative of this, I'd have to take the quotient rule. And in using the quotient rule, I also have to use the sum rule. And I also have the chain rule involved. But I can use the properties of logarithms and say this is the natural log of x. This is a product, so we make that the sum. So plus, here is something to a power, 2 natural log of x squared plus 1. Now I'm dividing. Well, this is to the 1/2 power. So I'm just going to say 1/2 the natural log of 2x cubed minus 1. Now when I take the derivative, I'm going to say, oh, the derivative of the sum is the sum of the derivatives, right? The natural log of x is 1 over x. So I'm going to get 2 times here. I want u prime over u. So if this is my u prime is going to be 2x over x squared plus 1. U prime over u, so that's going to be 6x squared over 2x cubed minus 1. And we can clean that up maybe a little bit. I got 1 over x plus 4x over x squared plus 1 minus 3x squared over 2x cubed minus 1. This one was a whole lot easier than having to deal with finding the derivative of this using the quotient and the product and the chain rule. So we can use our logarithms to kind of help us out when we do that. Now here's the real cool one. When we look at this one, we can do this right now because it's, well, this is something like a nasty problem I gave you in chapter 2. Because again, we have the quotient rule and we have the chain rule, and we can work through and do that. But we're going to use logarithms to help us do this, and we're going to take the log of both sides. And that's why we have to have this right here. Because if I don't have this, I can't take the natural log of both sides. Because if x equals 2, f of 2 is 0, and I can't take the natural log of f of 2, because I can't take the natural log of 0. But if I have this limitation on here, I can take the natural log of both sides to do this. So let's give this a try. And I'm going to want a little bit more space to do this, I think. So my problem was f of x equals x minus 2 squared over square root of x squared plus 1 when x does not equal 2. And the suggestion was, let's take the natural log of both sides. So we take the natural log, and instead of to make things easier, I'm going to make this a y instead of f of x. I don't want to keep on writing f of x. So, and I'm going to make this x squared plus 1 to the 1/2. Just to, again, make things a little easier for me to do. So this gives me the natural log of y equals the natural log of x minus 2 squared over x squared plus 1 to the 1/2. So let's plop in our properties. Natural log of y equals 2 times the natural log of x minus 2 minus 1/2 the natural log of x squared plus 1. Now we're going to take the derivative of each side. And the derivative of the natural log of y is going to be y prime over y. Derivative of here, we got 2 times the derivative of x minus 2 is going to be 1 over x minus 2. Here we have 1/2. Derivative of x squared plus 1 is 2x. Divide by x squared plus 1. So I'm just going to play with this side a little bit. 2 over x minus 2 minus x over x squared plus 1. So we'll make a common denominator here. So we'll go x squared plus 1, x squared plus 1, x minus 2, x minus 2. I got 2x squared plus 2 minus x squared minus a negative 2x is plus 2x. Give myself a little room to work. Over x minus 2, x squared plus 1. So that is x squared plus 2x plus 2, x minus 2, x squared plus 1. So that's y prime over y. I want y prime. So I'm going to multiply both sides by y. What was y again? Y is this x minus 2 squared over square root of x squared plus 1. So we got x. I forgot what that was already. I'll look at my paper. X minus 2 squared over, I'm going to just go x squared plus 1 to the 1/2. And we're going to multiply that times x minus 2 times x squared plus 1. And up here we take that times x squared plus 2x plus 2. And x minus 2, one of those cancels. And I can put here, those are both x squared plus 1s. So I can make this my derivative. So my f prime of x is x minus 2 times x squared plus 2x plus 2 divided by x squared plus 1 to the 3/2 power. Now, again, you can do this with the quotient rule and the chain rule and work this through with your, square root of this times the derivative of this minus this times the derivative of that divided by this squared and simplify it out and work those out. Or you can make it into these logs. That makes it go really quick. But yeah, we had to play a little bit with our fractions again to simplify things out. It's not too bad of a problem either way, but hopefully this way you can see that sometimes just using this trick of taking the natural log of both sides can get it down to a problem that's easier to work with. And if I didn't need it in simplest form, I could just at this point, I could have come along and said, oh, y prime equals, let's go that x minus 2 squared over x squared plus 1 to the 1/2 times 2 over x minus 2 minus x over x squared plus 1. You could bring that over at that point and then say, yeah, good enough. That's something I can work with and plug in with. Or you could try to simplify at this place, whatever floats your boat on here. But this is a way to sometimes make some of these nasty looking ones. A way to avoid the quotient rule if you want to avoid the quotient rule using logarithms. Oops, I didn't want this. Let's get this off here. So, last thing I'm going to hit here. This has been a long video, but we're getting into just one long video. The derivative of the natural log, the natural log is only defined where the function is positive. We can't take the log of a negative number. So sometimes we just use the absolute value. So we take into consideration what happens if we have negative values in there. But same thing, we're just saying as long as u is not 0, the derivative of the natural log of the absolute value of u is u prime over u. So here is some homework problems to do on the natural log function.